All right, so this is Unit 2, Lesson 4, Rates of Change and Tangent Lines. So the average rates of change, so we encounter average rates of change in such forms as average speed, growth rates of populations, and average monthly rainfall. So the average rate of change of a quantity over a period of time is the amount of change divided by the time it takes. So in general, the average rate of change of a function over an interval is the amount of change divided by the length of the interval. Okay. So looking at example 1, finding average rate of change. Did something. Okay. So for example number 1, find the average rate of change of f of x equals x cubed minus x over the interval from 1 to 3. So basically my solution is I'm going to take f of 1. So 1 cubed minus 1 is 0. And f of 3 cubed is 27 minus 3 is 24. And then the average rate of change over that interval from 1 to 3 is f of 3 minus f of 1 over 3 minus 1. So 24 minus 0 over 2 equals 12. So experimental biologists often want to know the rates at which populations grow under controlled lab conditions. So this figure below shows how the number of fruit flies, or Drosophila, grew in a controlled 50-day experiment. So the graph was made by counting flies at regular intervals, and then plotting the points for each count, and then drawing a smooth curve through those plotted points. Can't guarantee, so they didn't necessarily count on day 11 how many fruit flies there were. They might have only counted at 10, at 20, at 30, or at 10, 15, 20, 25, things like that. So they drew those lines kind of guessing where those points would be, but knowing that they were somewhere in between those. Okay. So example number 2, growing Drosophila in a lab. So I want to use the points 23, 150 and Q 45, 340 in that figure to compute the average rate of change and the slope of the secant line, PQ. So there were 150 flies on day 23, that's what this means, and 340 flies on day 45, that's what the Q means. This gives an increase of 340 minus 150, or 190 flies in 40 equals 22 days. Okay. So I found the change in my y values and the change in my x values. So change of p over change of t is 190 over 22, or about 8.6 flies a day. You can't have 8.6 flies, so you round up to 9. So about 9 flies a day. So the average rate of change is also the slope of the secant line through the 2 points P and Q on the population curve. So we can calculate the slope of the secant PQ from the coordinates of P and Q. So the change of P over the change in T gives me 8.6 flies per day, so that is my slope. So we can always think of an average rate of change as the slope of the secant line. So in addition to knowing the average rate at which a population grew from day 23 to day 45, we may also want to know how fast the population was growing on, specifically on day 23 or any day itself. To find that out, we can watch the slope of the secant PQ change as we go back, Q along the curve towards P. Okay, so here we start with the secant line at P. Here it is at another point, at a second point, at a third point, and then finally at P itself. So the results for 4 positions of Q are shown in this figure right here. So in terms of geometry, what we see as Q approaches P along the curve is this. The secant PQ approaches the tangent line AB that we drew by I at P. Okay, so that's basically the tangent. This means that within the limitations of our drawing, since we're not expert artists or anything, the slopes of the secants approach the slope of the tangent, which we can calculate from the coordinates of A and B to be 350 minus 0 over 35 minus 15, or 17.5 flies per day. In terms of population, what we see as Q approaches P is the average growth rates for increasingly smaller time intervals approach the slope of the tangent to the curve at P. So the slope of the tangent line is therefore the number we take as the rate at which the fly population was growing, specifically on day 23. Okay. So the secant slope is the rate of change over time, and the tangent slope is that rate for that specific time or day. Okay. So why are we finding tangents to curves? So in mechanics, the tangent determines the direction of a body's motion at every point along its path. Okay, so here's my path of motion, position of body at time t, and then here's my tangent, which is the direction at time t. In geometry, the tangents to two curves at a point of intersection determine the angle at which the curves intersect. Okay, so you can see that they intersect right there. In optics, the tangent determines the angle at which a ray of light enters a curved lens. The problem of how to find a tangent to a curve became the dominant mathematical problem of the early 17th century, and it is hard to overestimate how really badly the scientists of the day wanted to know the answer. So Descartes went so far as to say that the problem was the most useful and most general problem, not only that he knew, but that he had any desire to know. Okay, so finding the tangent to a curve basically came about with Pierre de Fermat, and he came up with steps in order to find this tangent. So basically, the moral to our fruit fly story, okay, would seem to be that we should define the rate at which the value of the function y equals f of x is changing with respect to x at any particular x equals a to be the slope of the tangent to that curve. Okay. But how do we define the tangent line at any point P on the curve and find its slope from the formula y equals f of x? This problem here is that we only know one point. So our usual definition of slope requires that we have 2 points, okay? Or at least 2 points, or we see the curve and we can pick 2 points. Okay. So Pierre Fermat found a solution in 1629. So it basically was probably one of the biggest contributions to calculus in that century. So we still use this method of finding tangents to produce formulas for slopes of curves and rates of change. And that's how, like, it was developed in 1629 and we're still using it now, okay? So step one, we start with what we can calculate. So we know the slope, we can find the slope of secant through P and a point Q, which is near the curve. Okay. Step two, we find the limiting value of the secant slope, if it exists, as Q approaches P along the curve. So basically we're taking the limit of that. Okay, we define the slope of the curve at P to be this number, and then define the tangent to the curve as P to be the line through P with the slope. Okay. So example 3 is finding the slope and tangent line. So I want to find the slope of a parabola, y equals x squared at the point P 2, 4. Okay, so we know the formula, we're given a point, and I want to write an equation for the tangent, the parabola to this point, at this point. Okay. So first thing I want to do is I want to begin with the secant line through the point 2, 4, and any nearby point that you would like. Okay. So in this case, I'm taking the x value of 2 plus h, and then that x value, and I'm squaring it. Okay. So 2 plus h squared on the curve. Okay. So here's my point. Here's my second point. We then can write an expression for the slope of the secant line and then find the limiting value, take the limit, of the slope as Q approaches P along the curve. So the change in y, 2 plus h squared minus 4, and then the change in x is h. Okay. H really doesn't change. H squared plus 4h plus 4 minus 4. The 4's cancel. From there, I have h squared plus 4h. I can factor out an h. Okay, so that gives me h plus 4. I take that limit as h approaches 0. The limit of h plus 4 equals 4. So therefore, the slope of the parabola at P is 4. The tangent to the parabola at P is the line through P2, 4 with slope m equals 4. So I use my point slope formula. Y minus 4 equals 4 times x minus 2. Y equals 4x minus 8 plus 4. So y equals 4x minus 4. So basically the tangent slope is f of a plus h minus f of a over h. That's how I find the tangent slope. Okay. So the slope of a curve, to find the tangent to a curve, y equals f of x at a point P, A, f of a, we use the same dynamic procedure. We can calculate the slope of the secant line through P at a point. Okay, we then investigate the limit of that slope as h approaches 0. If the limit exists, it is the slope of the curve at P, and we define the tangent at P to be that line through P having this slope. Okay. So slope of a curve at a point, the slope of a curve y equals f of x at the point P, A, f of a is the number m, slope, equals the limit as h approaches 0 of f of a plus h minus f of divided by h. Okay, of course, provided that the limit actually exists. The tangent line to the curve at P is the line through P with this slope. Okay. So once I have my slope, I create the line using the points that I have. Example 4, exploring slope and tangent. So I want to let f of x equal 1 over x. I want to find the slope of the curve at x equals a. Where does the slope equal negative 1/4? And what happens to the tangent to the curve at the point a, 1 over a for different values of a? So the first thing I want to do is find the slope at x equals a. So I substitute it in. I have a plus h minus f of a. So f of a plus h is 1 over a plus h minus 1 over a. I need to, of course, simplify that, which gives me the limit as h approaches 0 of 1 over h times a minus a plus h over a times the value of a plus h. Simplify some more. I have the limit as h approaches 0 of negative h over ha times a plus h. Of course, I can eliminate an h, which is great. Always positive to be able to do that. I substitute for h, and when I solve this, I have the limit of negative 1 over a squared. So as the limit of h approaches 0, I get negative 1 over a squared. So that's my slope. I want to know when the slope will be negative 1/4. So I set the slope I just found, the negative 1 over a squared, equal to negative 1/4. I solve for a and I get plus or minus 2. So the curve has the slope negative 1/4 at the 2 points, 2, 1/2, and negative 2, negative 1/2. So the slope of negative 1 over a squared is always negative as a approaches 0 from the right. The slope approaches negative infinity and the tangent becomes increasingly steep. Okay, we see this again as a approaches 0 from the left. As a moves away from the origin in either direction, the slope approaches 0 and the tangent becomes increasingly horizontal. So the expression f of a plus h minus f of a over h is the difference quotient of f at a. So suppose that the difference quotient has a limit as h approaches 0. If we interpret the difference quotient as a secant slope, the limit is the slope of both the curve and the tangent to the curve at the point x equals a. If we interpret the difference quotient as an average rate of change, the limit is the function's rate of change with respect to x at the point x equals a. This limit is one of the 2 most important mathematical objects considered in calculus. We will begin a thorough study of it in chapter 3. Okay, so basically we're going to start learning about derivatives in chapter 3, which is super fun. Okay. You get to manipulate all sorts of different equations. All right, normal to a curve. So one thing about the word normal, when analytic geometry was developed in the 17th century, European scientists still wrote about their work and ideas in Latin, the one language that all educated Europeans could read and understand. The Latin word normalis, which scholars use for perpendicular, became normal when they discussed geometry in English. Just so you know. So basically what we're saying is this line is perpendicular to the curve. Okay. So the normal line to a curve at a point is the line perpendicular to the tangent at that point. That's why we say normal to the curve and not perpendicular to the curve, because Latin. All right, example 5, finding a normal line or a perpendicular line. Okay. So one thing about perpendicular lines, we can create a perpendicular line based off of a slope, and we find the negative reciprocal of that slope, and that's how we determine a perpendicular line, if a line is perpendicular. So I want to find a normal line, so I want to write an equation for the normal to the curve f of x equals 4 minus x squared at x equals 1. So I need to find the slope of the tangent to the curve at x equals 1. Okay. So the limit as h approaches 0 of f of 1 plus h minus f of 1, because x equals 1, over h is, okay, so we're going to take that x equals 1 and we're going to substitute it in for the a value. So the limit of h approaches 0 of f of 1 plus h minus f of 1 over h equals the limit of h approaches 0, 4 minus 1 plus h squared minus 3. So I took this, I substituted 1 plus h and 1 in. When I simplify this, I get 4 minus 1 minus 2h minus h squared minus 3, which gives me negative h times quantity 2 plus h. Of course, I can simplify this by eliminating this first h here. So I have 2 plus h. Well, the limit as h approaches 0 is going to be negative 2. So I have negative 1 out front. So therefore, the slope of the normal is 1/2. The negative reciprocal of negative 2. Okay. So again, I take this slope. The reciprocal of it is 1/2, and then I make that negative, so it's already negative, so it becomes positive. So normal to the curve of 1, f of 1 equals 1, 3, is the line through 1, 3 with a slope m equals 1/2. And then find that line, y equals 3, or y minus 3 equals 1/2 x minus 1, which gives me the line y equals 1/2 x plus 5 over 5/2. All right, going back to speed. Function y equals 16t squared that gave the distance fallen by a rock in example 1 in section 2.1 was the rock's position function. So a body's average speed along a coordinate axis. So in our case, it's usually the y-axis, because when we draw with in a two-dimensional plane, we have an x-axis and a y-axis. So if we're falling, we're on the y-axis for a given period of time is the average rate of change of its position, y equals f of t. Its instantaneous speed at any time t is the instantaneous rate of change of position with respect to time at time t, or the limit as h approaches 0 of f of t plus h minus f of t divided by h. So we saw in example 1 that the rock's instantaneous speed at t equals 2 seconds was 64 feet per second. So example number 6, instigating a free fall. So I want to find the speed of the falling rock in example 1, section 2.1 at t equals 1 second. So the position function of the rock is f of t equals 16t squared. That's the formula that they gave us. The average speed of the rock over the interval between t equals 1 and t equals 1 plus h seconds was f of 1 plus h minus f of 1 divided by h, which gives us 16 h squared plus 2h over h. So when I simplify that, I can also take an h out of that. And I can eliminate the h on the numerator and the denominator, which gives me 16 times h plus 2. So the rock speed at the instant t equals 1 is the limit of, as h approaches 0, of 16 times h plus 2, well, t equals 1. So when I do that, 16 times 2 is 32. Because h equals 0, so 16 times 2 gives me the 32. And that is the end of Unit 2, Lesson 4. It's also the end of Unit 2.